Well, welcome everyone. We'll wait just a little bit to get started. We usually start 1 minute after the hour. Okay, why don't we go ahead and get started? You ready, Jeff? Welcome to the Air Sea Fluxes from Space webinar series. Today, I guess it's our Earth Day edition, and to broaden perspectives, we have economist Jeff Shrader from Columbia University's School of International and Public Affairs, who's going to talk about the mortality value of accurate weather forecasts. Jeff did a PhD in economics at UC San Diego, where he worked extensively with people at Scripps Institution of Oceanography. So he has a broad perspective on weather and climate and how scientists use information. And he has put this to work assessing the value of weather forecasts. So I'll let you take it away, Jeff.
All right. Well, thank you very much. And yeah, thanks for the opportunity to talk to you all. I am an economist by training, so I'm happy, maybe if the stuff I'm saying is a little out of left field, I'm happy to have a discussion afterwards. But my talk will focus on some recent work that I've been doing with co-authors on trying to understand the economic value of weather forecasts in particular, so short-range weather forecasts, and really how that helps or facilitates avoiding mortality from extreme heat. But I'll start the talk off in a second by talking about some broader work that's being done across the economics research community on the overall economic value of weather forecasting. Before I get to that, I'll thank a few people. So the NSF has funded this work. The art in the background of this slide and on a couple other slides is by my wife, Julia Bloom. So I have to thank her, and also in the background of my Zoom image here. And then the work itself that I'll talk about today is really coming out of two papers that I've been working on with a few co-authors, Laura Buckinson at University of Oregon, Derek Lemoyne, who's at Arizona, Manuel Linsenmeyer, who's a postdoc at Princeton, and then Stefan Thies, who's a PhD student of mine here at Columbia. So I want to start by actually talking about broad literature that's happening right now in economics on, I kind of grandiosely call it the new economics of weather forecasting. Just over the last few years, there's been this minor explosion of research on trying to understand the effect of weather and climate forecasts on economic behavior, and then trying to really understand the economic value of improvements in these forecasts or offering these forecasts at all. So there's an older literature on the economics of weather forecasting that we're really building off of, and I'll compare and contrast this new literature versus that old literature in a second. But a lot of the new literature originated, for me at least, with work I was doing trying to understand seasonal forecasts. In particular, I started out working on El Nino Southern Oscillation forecasts and how that helped fishers in the Pacific albacore and other tuna fisheries avoid damages from climate variation from ENSO. So that was work that I did when I was at Scripps. And then I have follow-up work trying to understand the effect of seasonal precipitation forecasts on construction, the projects I'll talk to you about today on mortality, and then a bunch of work by other authors now. It's really starting to grow very fast. And here's just a few of the papers. So people looking at hurricane forecasts and disaster recovery. So basically how it helps FEMA and also helps other people, by Molina and Rudick. A really interesting paper by Anand looking at snow early warnings and how they help prevent car crashes, especially as they come a lot earlier. A recent publication by Song looking at labor supply in China, and then a really cool experiment that was concluded last year by Fiona Burlig and co-authors looking at providing experimentally monsoon forecasts to farmers, in this case in India, and seeing if that helped them make better farm allocation decisions. This is just a flavor of the new research that's going on in this area. And there's really lots and lots of research growing all the time on this topic. And so just as a quick compare and contrast, you all might be familiar with earlier work that's trying to estimate the economic value of improvements in weather forecasts or the existence of weather and climate forecasts. This newer work that my research fits into in contrast to that work, is really focused on trying to bring large-scale data sets to the table. So we'll talk about my particular series of projects today, which are really trying to look comprehensively across the entire United States at weather forecasts and different economic outcomes. And then most importantly, from a conceptual standpoint, we're really trying to understand how changes in weather forecasts affect economic behavior while making minimal assumptions on the kind of decision making that people are engaged in when they receive these forecasts. So a lot of the earlier work on the economic value of weather forecasts in the 90s or before was using theory models. You might be familiar with cost loss models, for instance, where you basically have something like a Bayesian decision maker who's taking in weather forecasts and then making some decision based on the signal from that forecast, and the forecast helps them make a better decision. That is a really helpful framework for thinking about decision making under uncertainty, for thinking about the value of weather forecasting, but it's imposing quite strong assumptions on the decision making framework. And what we're trying to do in this new work is really just go out into the world, see how changes in weather forecasts statistically relate to or causally relate to changes in economic activity, and then go about trying to value the relationships that we find. So we'll see an example of that, or a couple of examples of that in the work that I'll present today. The bottom line from a lot of this work is that we're uncovering, I would say, tremendously high values for improvements in weather forecasts. That's true for short-range weather forecasts that I'll talk about. That's true for seasonal forecasts, like the randomized controlled trial in India. And there's less work on kind of climate scale forecasts, but I think that's going to be something that people are going to look more at in the future. But even there, we have a couple of papers that are showing that those help, for instance, financial market analysts make better decisions. So overall, I think we're uncovering, using this newer literature, some really large economic value from the existence and improvement of forecasts across different forecasting horizons. All right, so with that as background, I want to talk about the specific setting of the papers that I'm going to talk about today, where we're focused on the relationship between short-range temperature forecasts and mortality. And we're really trying to answer two research questions. The first is looking back into the recent past, how many lives have been saved by more accurate temperature forecasts that we've seen appear in the US over the last, say, 10 to 20 years. We start at the time we do because of data availability, but then we're really trying to understand over the time period that we can analyze how many lives have been saved by more accurate temperature forecasts looking back in the past. And then the second question, once we understand that relationship, is to look prospectively into the future and think about the potential role of even short-range weather forecasts as a facilitator for climate adaptation. So as the climate changes over the coming, say, 75 years or more, forecasts are also likely to evolve. And so will further forecast improvements, or do we expect those to help offset some of the mortality consequences of climate change? What would it take basically in terms of forecast improvements to realize, to offset some of those damages? So how effectively will forecasts allow people or help people adapt? You know, I don't know that I need to motivate these questions too much, but I'll just say that the narrow focus on mortality and temperature forecast is driven by a couple of things. One is right now around the world, a very large fraction of total mortality is at least partly attributable to temperature, to suboptimal temperatures that are either too hot or too cold. So if you look in the United States, you know, acute temperature exposure leads to probably about 1% of all mortality in the United States. So 1% is not a big number in percentage terms, but that's a very large cause of death if you look at total causes of death. And the US is relatively well off in this regard. If you look at other places like even Mexico, right across the US border, it's something closer to 9% of all deaths are due to both hot and cold temperatures. And so that's really what motivates us, my research group, to go and look at how effectively, what role forecasts can play in helping people or help society try to avoid these temperature-related mortality events. And then on the prospective question about climate change, Right now, our current projections, if you go and look at, for instance, the most recent EPA social cost of greenhouse gas report, they suggest that the majority of monetized climate change damage in the future actually comes from temperature-related mortality. In their analysis, in some cases, up to 70% of the total damage, economic damage from climate change is just coming from acute mortality due to changes in temperature. So really important, I think, to both understand it in the past and also understand this relationship in the future. And so what we're going to do to try to understand these questions is really in keeping with this style of the new economics of weather forecasting literature. We're going to combine comprehensive data on mortality in the United States over about a decade, almost 2 decades, records on temperature exposure for the population across the United States, and then a comprehensive set of weather forecasts, short-range weather forecasts from the National Weather Service. We're going to put all of those pieces together, and then we're going to construct statistical models that relate mortality to forecasts while controlling for a bunch of potential confounders so that we can try to isolate the causal effect of more versus less accurate forecasts on mortality. So you should think that the empirical exercise we're going to do is conditional on a bunch of controls. On a day when the forecast is idiosyncratically in error versus accurate, how high is mortality? So how much higher is mortality on the day when the forecast is quasi-randomly in error versus accurate? If it's higher on the day when the forecast is in error than when it's accurate, then there's scope for reducing mortality by making forecasts more precise, by reducing those errors. So that's the game plan for what we're going to do in terms of the research design. So I'll describe the data, describe the empirical approach, and then we can get to the results. So on the data side, we're putting together these three main ingredients. We have data on mortality from the Centers for Disease Control. They provide comprehensive records of all-cause mortality in the United States at the county day level. So we know we have records of every person who experienced a mortality event. We know the day that they died, and we know the county in which they died. And we have those records for an 18-year period, so 2005 to 2023. We aggregate those records into daily county level mortality rates. And so the unit of analysis throughout is going to be at the county level, where our main outcome variable is deaths per 100,000 population, so the mortality rate at the county level on a given day. So that's our main outcome variable, mortality. We're going to match that with data on realized weather. We're going to be focused on temperature in the analysis I'll talk about today. That's for these kind of climate change related reasons, and also just we see from the prior literature from epidemiology and economics that temperature is a major driver of mortality. And then in everything I'm going to show you today, we're controlling for precipitation, but it's not the main focus of what I'm going to talk about. We're going to take our realized weather data from PRISM. So this is derived from station observations and then interpolated using a regression model, but we can use a variety of different sources for our realized weather. This is just one convenient source. And we're going to take the gridded PRISM data and we're going to aggregate it to the county day level using population grids. So we know where people live inside a county, and we're taking the PRISM weather observations and weighting them more heavily inside the county based on the population density across the population grid in the county. So we end up with mortality rate at the county level, at the day level, and then we have average temperature and cumulative precipitation at the day county level as well. And then the final ingredient is to add weather forecasts. For both of the analyses I'll show you today, we're focused on the weather forecasts that come from the National Weather Service and from their National Digital Forecast Database. So these are the forecasts that appear on the National Weather Service website. And given the audience, I don't need to describe the process for creating these, but when I talk to economists, I have to emphasize that this is the result of a bunch of different inputs on the meteorology and forecasting side, right? So this is not just the raw numerical prediction models, but these are actually the kind of final end result forecasts after the National Weather Service meteorologists take in those models, use their expert judgment, and create the improved forecast that then gets issued to the public. So we're taking NDFD forecasts. We're focusing on short horizon forecasts of temperature. So everything I'm going to show you today is either 1 or 3 day ahead temperature forecasts. I'm happy to talk about why we choose to analyze those very short horizon forecasts later, but that's going to be the focus for this particular talk. And again, we do the same aggregation procedure as we do for the weather realizations, so that we're doing a population weighted aggregation to the county day level for average temperature forecasts and forecasts of cumulative precipitation as a control. Okay. So we put all those pieces together on the data side and put them into a flexible statistical or econometric model that I'm depicting, the estimating equation here, but I'll talk through it, where we are relating as our outcome variable mortality rate, so mortality rate M in county C on day T, to flexible functions of, here in this F term, realized temperature in a county on a given day, and forecast errors in a county on a given day. We allow realized temperature and forecast errors to interact. So we're estimating the surface relating mortality to temperature and forecast errors. So we allow basically forecast errors to have a different effect on mortality at different levels of temperature by estimating these spline bases over temperature and forecast errors. And I'll show you how the estimation results look in a second, but the basic idea is that for the core piece of the estimating equation, we're just relating mortality on a given day in a county to this flexibly estimated surface of temperature and forecast errors. And the idea is we want to look at, as I said before, days when forecasts turn out to be in error versus turn out to be accurate, and ask whether mortality is higher on those days when forecasts are in error versus when they're accurate, to try to understand the scope for saving lives by reducing forecast errors. So that's the core piece of the right-hand side of this equation, is this flexible function of temperature and forecast errors. We're estimating a distributed lag model, so that's the summation here. So we're estimating this in the baseline results over a week's time. This is to account for what the epidemiology literature would call harvesting, or what economists might call intertemporal spillovers. Basically, if there's high temperatures, for instance, on a given day, what we observe is that mortality is elevated on that day, but then over subsequent days, mortality is actually, if anything, a little lower than you'd expect. So excess mortality goes down a little bit over subsequent days. And that's, there's this offsetting or displacement of mortality events over time. So we want to capture the cumulative effect of temperature and forecast errors, accounting for that temporal displacement of mortality events. And then everything else in the regression are controls, so that hopefully we're isolating causal impacts of forecast errors on mortality. So we control for realized precipitation and forecasts of precipitation flexibly. We control for a bunch of things at the county and day level. So for instance, county specific seasonal patterns are controlled out of the specification. So we know that forecasts tend to be more accurate at some times of year than others. We know that mortality tends to be higher at some times of year than others. But that seasonal pattern might not be due to, or that seasonal relationship might not be due to the forecast related to mortality, but due to other factors. And so we want to control that out and isolate plausibly exogenous variation in forecast errors, and relate that to the excess mortality in a county on a given day relative to what you'd expect for that county in that time period. All right. So I can also happy to take questions more questions about this estimating equation later as well. But again, coming back to this basic idea, we're going to try to relate excess mortality, so unexpected mortality events in a county on a given day, and see how much that is due to forecasts being accurate versus inaccurate in a quasi-random way. So when we fit this model, we estimate this surface, and here's the summary of this fitted surface showing the effect of forecast errors on mortality. So I'll show a couple different takes on how we estimate this, but this is one way to visualize the estimates we get from fitting that regression. So all of these estimates, all of these points in this figure come from one run of that regression on our data on mortality, temperature, and forecasts for our 18-year period. So on the x-axis here, we have different temperature bins or different temperature levels. So we're thinking about average temperature in the day. So 30 degrees Celsius average temperature in the US, that's about the hottest 1 or 1.5% of days in the United States. The average temperature in the US is closer to this 15 to 20 degree bin. And then we go all the way down to temperatures below freezing. And then we're looking across that temperature range at how forecast errors affect mortality. That's the y-axis here. So these are the coefficients on our forecast error dimension of that spline basis. And each point is showing the effect of forecast errors in different directions on mortality. And we have for the blue points, the effect of the forecast being too cold relative to the realization, and the red points are showing the effect of the forecast being too hot relative to the realization of temperature. And then the point is telling you how mortality changes in the event that the forecast is 1 degree too cold for the blue point or 1 degree too hot for the red point. And so we can focus here on this hot temperature bin, so days when the temperature is forecasted to be 30 degrees C or higher, we find that a forecast error on that's too cold leads to really elevated mortality, and a forecast error that's too hot basically on average doesn't have any effect on mortality. And so if you want to see that in terms of predicted excess mortality coming from our model, this is the model that just uses a linear spline on either side for positive and negative forecast errors. Basically, what these points are implying is that when you have a negative forecast error, so a forecast that's too cold, you have elevated excess mortality. And when you have a forecast that's too hot, you don't have really any elevation of excess mortality. And so this is first telling us that forecast errors do have a significant effect on mortality, but two, that effect is asymmetric in a way that is maybe intuitive. Where on a hot day, it's a hot day, when the forecast says it's going to be colder than it actually turns out to be, then the forecast is saying, oh, it's not going to be that hot. And so people might go out and engage in behavior that's riskier. They might, go and garden outside or something. But then they end up being exposed to these very hot temperatures. And that elevates their mortality. Versus over here on the right-hand side, the forecast is saying that it's going to be even hotter than it turns out to be. And so on those, it's plausible that people are, seeing this forecast. They're not going outside as much. They're taking more precautionary behavior. Emergency response is being activated more based on this forecast. And so even though it turns out to be quite hot, it's not as hot as the forecast said it would be on this right-hand side of the curve. And so mortality is not elevated there. So there's this asymmetric effect of forecast errors on mortality, where really forecast errors that are too optimistic raise mortality, and forecast errors that are too pessimistic on average don't have much of an effect on mortality. So this effect is especially strong for this hot temperature region, for this area where the forecasted temperature is expected to be 30 degrees or hotter, but we see a similar pattern actually across the range of warm and hot temperatures. So all the way down to 20 degrees Celsius, we see that negative forecast errors elevate mortality. Positive forecast errors have a weaker effect on mortality. Although by the time you get to this 20 to 25 degree bin, the distinction between those is not statistically significant. You get the flipped pattern as you go to cold days. Again, this is potentially intuitive, where here, if the forecast says it's going to be warmer than it actually turns out to be, maybe people go and engage in riskier behavior. The temperature turns out to be very cold, and then they experience excess mortality, whereas the opposite is not true if the forecast says it's going to be even colder. So across the board, we find that for very cold and warm or very hot days, forecast errors elevate mortality. The important converse of that is if you were to bring forecast errors down, if you were to, say, make forecasts more precise, shrink the distribution of forecast errors, you would save lives, according to this model. We would predict that lives would be saved. And so that's the exercise we carry out in that first paper. We look at the historical record in the US at NDFD forecasts, and we calculate the root mean squared error of day-ahead temperature forecasts across the entire US and see how they've trended. So here I'm fitting local linear regressions to the root mean squared error of forecasts in the US over our sample period. And we see that for cold, cool, warm, and hot days in blue, green, and then red, respectively, forecast errors have fallen on average. So root mean squared error has gone down over our sample period, and it's gone down quite a bit. So if you look over a 20-year period, forecast errors have gotten about 45% smaller for these day-ahead temperature forecasts. So if you run that change in forecast errors through our fitted statistical model, keeping track of the fact that that forecasts have different effects for cold and hot versus warm and cool temperatures, you end up with this kind of punchline for that first piece of the analysis, which is, I'll just focus on this bottom number here, a 50% improvement in forecasts, so a 50% reduction in the root mean squared error forecast we find saves over 2,000 lives. And so empirically, we've seen about a 45% improvement in forecasts over the last 20 years in the US. And so our kind of bottom line number from that first paper is that forecast improvements over the last couple of decades are likely at this point saving north of 2,000 lives per year in terms of reduced temperature-related mortality. That's coming, partly from very hot days, but those are quite rare. And so interestingly, it's coming actually mostly from these warm or hot, but not extremely hot days, just because those are so common. Okay, so that's looking back in history at the recent history of the US and how forecasts have evolved and likely affected mortality from temperature. The next question we want to answer or ask is how this relationship is going to evolve in the future under climate change. And so we're really motivated to think about this because of the potential role of forecasts as a facilitator for climate adaptation. And then also, me and my co-authors, we were just really curious how meteorologists thought climate change might affect forecast quality. Do they think that it's going to, push us out into a world that's harder to forecast? Is it going to make forecasts, easier for some reason? Is it going to have basically no effect? And so the crucial thing that we need to add to our analysis that we already did is to understand how both temperature and forecasts are going to evolve under climate change. So the first part of the empirical analysis is to relate forecasts and temperatures to mortality. So this is estimating the same type of statistical model I showed you before, but I only showed you the effect of forecast errors on mortality in the results before. This figure is now summarizing the effect of both forecast errors and temperature on mortality. I think the easiest part to interpret is this right panel here, this panel B. We have average daily temperature on the x-axis. We have excess mortality on the y-axis. Each line is showing you the relationship between temperature and excess mortality for a given level of forecast error. So the orange line here is showing you the relationship between realized temperature and mortality on days when forecasts are accurate. The purple line is showing you what happens when the forecasts have a 2 standard deviation error. So a rare but not atypical forecast error. And you see the effect that we saw before, which is especially on warm and hot days, mortality is much higher if the forecast is an error compared to when it's accurate, comparing this purple and yellow line. And then you also now see the relationship between temperature and mortality. So basically, cold temperatures lead to excess mortality, hot temperatures lead to excess mortality, and forecasts are especially valuable on warm and forecast improvements are especially valuable on warm and hot days. So that's like summarizing the full relationship between temperature and forecast error on mortality in one figure. So now what we want to do to think about climate counterfactuals is take these fitted curves and think about how the distribution of temperatures down here is changing, so how that's shifting under different climate scenarios, and how forecasts are changing in the future. Climate scenarios we can get from standard climate projections. We use GFDL projections for that exercise. The novel thing we're adding is projections of future forecast errors. And we get those, we issued an expert elicitation of what operational meteorologists thought future forecast errors would look like in 2050 and 2100. We issued this expert elicitation among public sector operational meteorologists in the US and Europe, in different countries in Europe as well. So if any of you on the call participated in that expert elicitation, thank you very much for participating. And so this figure is summarizing the results of that expert elicitation. Basically, we have time going from our sample period at the beginning out to 2100, and we have the projected root mean squared error of temperature forecasts. We see the historical trend in forecast errors that I showed you before. It's basically forecasts are improving a lot over the last, say, 20 years. And then these violin plots are showing the projections that our experts gave for how forecasts would evolve in a median scenario in the middle, and then a upper 95th and lower 5th percentile scenario as these other two lines. You can see the full range of expert elicitation answers for the 2100 answers over here on the right. But basically, our experts believed, if you follow this green line, that forecasts would continue to evolve and continue to improve in a central scenario and be about 22% better by 2100. So there would be improvement, but it would be slowing relative to what we've observed over the last 20 years. But they entertain some possibility that there would be accelerated progress or that progress would essentially stagnate. So we can now take all of these ingredients, our fitted surface relating mortality to temperature and forecast errors, and see what happens as temperature changes, see what happens as forecast errors change between now and 2100. And that'll be my the last piece, my last piece of the presentation. So we're summarizing those effects on this in this figure here. And we're working on the language because I think it's a little bit tough to communicate this, but basically what we're thinking about is trying to split future mortality from heat up into two components. One is the component that comes from perfectly accurate, perfectly forecasted temperatures. That's what we're calling the expected temperature component here. And so if we just focus on this left column, going down the column, we have different climate scenarios, so different warming scenarios. And we can see that under a moderate warming scenario, so SSP 245, we're projecting about 2,000 more lives lost per year from heat in the United States. And then as we go up to SSP 585, that number goes up more than 4 times, so 8,000 lives lost in the US per year from heat in the climate change counterfactual compared to the no climate change counterfactual. So these are excess deaths due to climate change by 2100. And that's in the condition where forecasts are perfectly accurate. And then we can layer on top of that mortality that's due to, so to speak, forecast errors. And so the total height of the bar here is the sum of that expected temperature mortality and unexpected temperature mortality, i.e. mortality that's statistically related to forecast errors. And then we look at that for a case where forecasts don't improve anymore from where they are currently, where forecast improvement continues but is slow, so the upper 95th percentile from our experts, the central projection from our experts, and then the aggressive improvement scenario from our experts. And I'll just point out a couple of things. One, by 2100, under the accelerated improvement scenario, or even under the continued improvement scenario for our forecasts, in SSP 245, forecasts are getting good enough that you're almost wholly eliminating mortality from heat-related mortality in the US. As you go down the column here, you can see that forecasts, even if they're rapidly improving in the future, they don't fully eliminate heat-related mortality due to climate change. But the magnitude of the change is bigger. So you're saving a lot more lives in levels as we think about these more aggressive warming scenarios, even though forecasts are not fully offsetting mortality due to heat. So the bottom line here is that in the future, further forecast improvements are really important for saving lives, and they actually get more important on an absolute level basis as warming is more aggressive, and they're essentially fully offsetting mortality due to heat in less aggressive warming scenarios. So I'll stop there. I think our work is basically just underscoring the real importance of forecasts and accurate forecasts for helping people avoid mortality from temperature, both in the past and the future. And I'm happy to take questions or have a discussion.
Thank you. This was great. Questions for Jeff? I see there's a comment in the chat from Fred Bingham,
Pull that up.
who asks, Fred, do you want to just go ahead and ask your question?
Yeah, sure. It's obviously more valuable to forecast excessive heat rather than cold. Um, you may not know the answer to this being an economist, but what would our observing system and our forecasting system look like if that were our goal?
Yeah. So I'll say a couple things from the econ side of this, and then I'm curious actually to hear your views on this. So one reason why we probably observe this pattern, right? So like, why do we basically observe that these curves here, for instance, are right on top of each other on the cold side, but there's this kind of big difference in them on the hot side? So part of this is just due to the fact that on the cold side, mortality is not coming as directly from temperature. So this is partly just the causality is not as clear on the cold side. So if it's hot outside, people experience acute mortality from the heat per se. The biology, biophysical, physiology literature points us in that direction. Whereas on the cold side, it's a more complex relationship. So there's infectious disease that's happening and maybe being helped by the cold. There is just a longer lag between exposure to temperature and when people experience mortality events. And so the causal chain is just more complex and long here. So partly what I'm saying is maybe we're just not picking up the total effect of forecasts on the cold side because we're just focusing narrowly on temperature forecasts. And if we were to look more holistically at temperature forecasts, precipitation forecasts, other things, maybe we would pick up some of those other effects that are coming through multiple channels or like overlapping weather events. So there's just a cleaner signal, higher signal to noise ratio on the hot side. That's one thing. Then returning to your question, your question specifically on the current observing and forecasting system. I would love to know the answer to this basically. Like, I think people pay a lot of attention to precip and temperature forecasts. We know this from psych literature, from econ literature. I don't know that people I just don't know how people process and use these cold weather forecasts and all the information they might need to avoid mortality on the cold side as well. And so I think it's just a more complex information environment. And then two, it just seems like people have a harder time adapting to cold. There's like more ready, easy adaptations that we can do as individuals or society on the hot side. So that's a little potpourri of answers. But I'd be curious actually from the meteorology side, how you all are thinking about this.
Good question. I see Christine Goman-Ginger has her hand up.
Oh, hi. Thanks. That was really interesting. Thank you very much. I have a couple of questions. The first one is I noticed that your improvement in forecasting seemed to be far greater for the extreme values of temperature, for the very low temperature and the hot ones. You can see the two green lines are not quite as steep. Do you know why this is? What is the reason
So
for this improvement in the extremes?
right. So yeah, it is absolutely the case. I mean, whenever we look at this, it is the case that we see this in the US. We see this globally. Actually, I work with Manuel and Samir showing something similar. So again, this is me. Okay, so I'll say what I think I know as an economist, but you correct me if I'm wrong. Okay, so the level difference is partly just coming from the challenge of forecasting cold temperature versus hot temperature, like the stability of air masses and things that are coming from convection. I'm going to really be out of my depth, but in the U.S. at least these hot temperature conditions, forecasts are better during hot temperature conditions because of these considerations around, basically atmospheric volatility and convection. Sorry, I'll stop there and I won't say any more meteorology. Now, but then why the faster improvement, the relative improvement is faster in the cold conditions than the hot conditions? I'd be curious to ask you. So my simple explanation has been that one, there's just more room for improvement on the cold side. We're not as close to zero on the cold side. And so just think about the percent change. You have kind of for a given level change, you're going to have a bigger percent change in the cold side. And then two, you're just much further away, just in a narrow mathematical sense from potential bounds. But then, of course, that depends on kind of the possible limits to forecastability. So yeah, it's an empirical regularity that we find in lots of places. But I'll actually ask you to tell me the meteorology, if you don't mind, about why you think we're getting this faster improvement on the cold side than on the hot side.
I don't know. I'm an oceanographer, so I leave this to the meteorologist online if they can. Yeah. I just wondered if it might have been something to do with the availability of observations, which is kind of what we're looking at in this particular webinar series. So I wondered if there was
good reminder. So I'll say a few things about observations. So I have work that's trying to look globally at forecast accuracy and precision changes over the last 40 years. And we're focused there mostly on numerical predictions from ECMWF, but we also do a little bit of analysis of GFS and the German Met Office's numerical model. And there, we find what lots of other people find, which is, of course, satellites are a major cause of the longer run changes in those. I don't know if satellites are going to be more helpful on the hot side than the cold side. I don't have any, I haven't read anything that would suggest that, but again, this is not, I am an economist. We do find, though, that, again, consistent with the literature, that some fraction, 5, maybe up to 20% of the improvement is coming, or sorry, the difference in levels across locations is coming from, ground-based stations and radiosones and things like that. So there is a role for observations to play. And then you've raised a really interesting question. Let me see if I have it. Oh, I don't have it in here. Sorry. I unshared my slides. We asked meteorologists in the US what they think would be the major, like basically what would cause forecasts in the US to not get better over time in the coming century. And they said very clearly that like the reason why you might, sorry, I'm flipping back to this slide. The reason why you might experience this blue line, for instance, they said was very much because of loss of observations. So they talked about AI being, and new model improvements and things like that, leading us to this yellow line potentially, just like the usual model improvements, but then also potentially some AI-driven model improvements, things like that. But the blue line, when we asked them, why might this blue line appear? The number one thing they said was loss of observations, both ground-based and satellite-based observations. And that came out really clearly in our expert elicitation.
Very good, very good. Just what we want to hear.
Exactly. That will be hopefully submitted soon. So
I have a second question, but I see that Rick has got his hand up. So perhaps, for interest of time, perhaps pass to Rick.
We can go to Rick and
come
then
back to
Christine,
me.
and
yes.
Carolyn Reynolds has a comment.
Okay, thank you. Thanks, Jeff. Great talk. Um, uh, Thanks for the insight. I have a question about whether, two questions, but maybe I'll save mine for after Christine, second one. So I have to choose one. The more direct question is whether in the projection at the end of the talk, the projections into the future, whether you're accommodating this hot model problem that people have seen in some of the CMIP6 models. Are you able to adjust for some of these models being too hot and therefore extremes being too high?
So, I'll say a couple. We aren't doing much adjustment at all here. We're debiasing in the way that, the simple debiasing procedure that everyone does relative to our observed, the delta-based debiasing in the pre-period. And then we're, in these projections, just using GFDL. So we're not using multiple models. We're not comparing across models to try to account for these types of biases. So you tell me if you how much you'd like to see that. I'm happy to go and dig into that. But the reason we were doing it is really just because the focus of this particular paper, sorry if I can go back, is this piece of the projection. So the forecast piece of the projection, because there have been good analyses before of just the temperature side of the projection, but not accounting for the fact that basically adaptation opportunities are changing on the economic side as we're moving into the future. And so this is taking those model biases on the temperature side kind of as given. So we might be overstating mortality due to heat if we have a hot model. I don't recall now off the top of my head if how GFDL behaves in this regard. But the main focus that we have is take that as given. How are the forecast accuracy changes affecting things? Now, I take the point absolutely, which is our forecast accuracy effects are dependent on the temperature as well. And so these two things are going to interact. So we should do a more careful job on that side. So I'll go download some more CMIP6 runs and and do that after this talk.
That's great. Christine should ask, and then maybe I'll come back with the effective climate sensitivity of the GFDL if I can find it quickly.
Sounds good.
All right. My second question was about if this type of analysis is also being done for longer time scales, because here I understand it's about forecasting to 3 days. But I can imagine that the impacts of forecasts can be even more significant on kind of seasonal and even decadal scales. But this is my knowledge as a scientist of economics is very limited. But I'm just curious to know whether these types of analysis can also be extended to longer timescales.
Yes. So thanks for asking the question. That's something I do like to talk about with a natural science audience. Because I think there's a little bit of unintuitive. There's something a little bit unintuitive going on here. So if you look at the research that's been done, it's been done basically on kind of a short range to a seasonal scale so far. And a lot across this list, but if you go and extend this list to kind of everything that's been done, by far the biggest effect that we find is the one I just showed you on mortality in terms of the monetized value. So the kind of monetized economic impact, the lion's share of that impact is coming from these day ahead temperature forecasts. So a couple of things about that. So in the full paper that we did on this, we've looked across the range of short horizon forecasts. So 1 out to 6 or 7 day forecasts. And if you just include all of those forecasts in the model at once, then what you find is that the day ahead forecasts are actually responsible for about 2/3 of the mortality improvement. And all of the rest of those forecast horizons share out the rest of the 1/3 kind of in a declining pattern. And so it seems like for mortality from acute temperature exposure, it's day ahead forecasts that are really, really helpful. And then you have this declining marginal value of forecasts at longer horizons out to the end of the short range, weather forecasting horizon, that National Weather Service issues. So that's all within short range, but that same kind of logic applies going even further out. So if you think about the economics of this, there's a really nice paper by Milner and Heian, which describes the theory of the marginal value of forecast horizon, economic value of increases in forecast horizon. And the idea there is that you should expect in general to find decreasing marginal value of longer horizon forecasts. And the logic is essentially that, people want to wait until the last possible minute to act, balancing a couple of trade-offs. One is that forecasts are getting better as you get closer to the event. Two, people are impatient, so they'd rather act closer to the event than further away from the event. But then the thing that's pushing back against that is people, if they're facing adjustment costs or frictions to their action, then they want to act further in advance. And it just so happens to be that our estimates of those frictions or adjustment costs, if you go out and estimate them in the economy, they're low enough so that really it's short horizon forecasts that are most helpful, probably. This is a theoretical statement from Milner and Heian. And longer horizon forecasts are valuable, but there's this kind of somewhat rapidly declining marginal value of forecast horizon. And so we're seeing that over short horizon. In this Downey-Lynn-Shrader paper, we're looking at seasonal forecasts out to 6 months. We see that same kind of decreasing marginal value of horizon out to 6 months. And nobody has, people have looked a little bit at longer scale climate projections and how those affect financial markets, but I've never seen somebody try to smoothly calculate the value out to those horizons. But I suspect the same thing again would hold, just because of these counteracting forces. You're going to tend to find that shorter horizon forecasts are economically more valuable on the margin. Okay, so
very counterintuitive indeed.
Yeah.
Yes, thank you.
Yeah. So
Thank
I
you.
shouldn't say, I want to end by saying it's not the case that longer horizon forecasts are not valuable. It's just that the most value comes from short horizon forecasts, and then the total value is coming from the full set of horizons. It's just that if I had $1 and I could make a forecast equally better at a 1 day ahead horizon or a 1 year ahead horizon, as an economist, I would have to say that I would invest that dollar, at 1 day ahead, although I know that a lot of that also you have to balance the ability for that dollar to actually realize returns to forecast improvements, which might actually happen more at longer horizons. Yeah.
Thank you very much. Thank you.
Yeah, very good question. Yeah, thanks for the question. So it's something I would be happy to discuss for a full hour with natural science folks and think about where the pros and cons or the costs and benefits are of improving in forecasts versus the economic value of those different horizons.
So I see Rick has put a comment in the chat about the GFDL model. Rick, do you want to just comment on this?
Okay.
Yeah, none of them that I could see are too hot. So it's a good sign that you're using it. An excellent reference there.
Okay. Yeah, I used it because of work that I've done with my climatology colleague, Adam Sobel, and others here at Columbia. And so he uses it, and so I used it, but I'm glad. Thanks very much for pulling that out.
Thank you, too.
And Carolyn Reynolds has put some comments in the chat. Carolyn, do you want to speak to those?
Yeah, sure. First of all, thank you very much for a great presentation. And I could look at that graph showing the improvements with time based on temperature, just coming up with all sorts of hypotheses as to what might be controlling those improvements. I think that's great. And I just a wild guess about the dip and the high temperatures might have to do with the going to higher resolution in the models and doing better job with the land surface, particularly for things like urban heat islands. And so that led into my question about if it would be possible to if the data has enough resolution to consider urban versus non-urban mortality, and that might project onto this idea of the first question about how forecasting and observing systems might change in the future. Thank you.
I love that question. So, okay, first of all, yes. So NDFD there's one resolution improvement that happened on the NDFD side, basically in the middle of our sample period. But then, of course, the input models, the numerical weather prediction input models are also changing over this time period. And so I'd be curious to go back and revisit when exactly those, when the GFS, for instance, when was their resolution change on that side. Because the NDFD, I think it was almost exactly in the, well, maybe the first third of this figure is 2010 or so, that they doubled their resolution. And we have been really curious to think about that. I hadn't tied it to this figure before, but we had been curious to think about that exactly for the reason you raised, which is, if you have a uniform grid for your weather forecast across the country, you're probably, serving well folks who live in areas where there's not very much of a, gradient in temperature across space, but that's not serving folks who live in places like urban areas necessarily very well, because we know there's this complex geography of heat in those urban environments. And so we have thought about it. We've written up a little bit of a paper trying to understand the value of forecast resolution improvements specifically for urban versus non-urban residents, exploiting this change to the NDFD that happened in the middle of our sample period. I wouldn't say that we found anything super duper, nothing's jumped out to us yet in that analysis, I'll say. But also it's one, I haven't dug in on the analysis as much as I would like. But we found a couple of things that are relevant to the discussion. So one, we do find that if you just go back to, this basic relationship here that we estimate, we find that people who live in urban areas on average are experiencing less benefit from forecast improvements. So forecast errors matter less for them, and the corollary is that a forecast improvement helps them less compared to people who are not living in urban areas. The thing that we haven't been able to do is then go and specifically tie that to a change in forecast resolution, because you'd expect that then the change in forecast resolution would help people who are living in urban environments. So that's the missing piece that we want to go and look for. And I think that would be really, really interesting to look at. And then I'm curious, it's you could imagine that the National Weather Service, for instance, could issue forecasts that are higher resolution for urban areas or for places with more complex temperature topography. I understand that that's going to, really potentially mess up the computational complexity. There are issues around that, around the implementation, but that's the sort of thing that I, as an economist, would be interested in comparing the pros and cons of that, because I do think there's a lot of value in making forecasts much higher resolution for some places in the country, but less high resolution in other places in the country. We've seen that in other areas, like pollution impact modeling, for instance, is an area where atmospheric chemists have pursued that strategy. So I think there's a lot of promise to that, just from an economic standpoint. I understand there are lots and lots of complexities on the physics side and the meteorology side that I'm not getting into.
Thanks so much.
Well, we're almost out of time. There's one more question in the chat. Megan Cronin asks, do people know why the errors increased in the 2012 to 2013 period?
No, I've asked about
0 to 30
this.
range.
Yeah, I've asked about this a few times. Every time I give a talk and there are some, meteorology or climatology folks in the room, I ask them about this exact bump, and I've heard different things, but I've never heard anything definitive about why there is that increase. I'll say if you look, I have a similar figure for ECMWF, just as example, pure numerical weather prediction, and there you also see some non-monotonicity, but it's not at the exact same time. It's not at the exact same temperature levels. So it's hard for me to then kind of say one definitive source, because it's not it's not a signal that's coming obviously necessarily to me just from looking at those two different things from the physics of the matter, but maybe something else. So I'm not wholly sure. I'll say one thing that I've been a little surprised by digging into the NDFD is how important individual meteorologists are at the National Weather Service to these NDFD forecasts. So especially in this pre 2017 period, the humans are driving a lot of the forecast accuracy for a lot of these forecasts in a way that I was surprised by based on my prior. I thought the machine would be doing a lot. and the human value add might be relatively low, but the human value add is really high. And then we also see across National Weather Service forecasting offices, there's quite a big difference in forecast accuracy. So I think bottom line is there's just a lot of possible explanations for why this might be going up or down, coming from the physics side, from the computation side, and from the human side. And I don't know. I'd love to know, but I don't know.
It's
Well-
it is interesting that is when the tropical Pacific observations dropped out. So,
Oh, interesting.
I'm just wondering.
That's interesting.
So it would be interesting to put a geographic assessment on that and ask if the
Yeah.
Those are
predictions
critical
got worse
for
on the
El
West
Nino.
Coast, where the tropical Pacific stuff had a more direct impact.
Right.
I can look at that because, you know, I started as an INSO person, and I was starting doing like INSO teleconnection analysis and things like that. So I can run that analysis. I'll say in general, if you all have ideas for specific times when potentially high value infrastructure came on or offline, and likely places where that would have had an effect on forecast accuracy, I would love to go and analyze that, because that's like the sort of thing that economists are really hungry to go and look at as a first stage, and then go and look at how that feeds into economic outcomes on the other side. Because one of the challenges that we have in the economics of weather forecasting is that weather forecasts are such a complicated production process, and there's so many inputs and things are rolling out slowly over time, that we very rarely see kind of sharp changes in forecast accuracy coming from a single identifiable source. And so if you all have thoughts like, oh, you know, a major set of buoys went offline for a certain period of time, and that likely had an effect on, say, like California precip forecast or something, I would be all ears for that type of variation, because then that allows us to say, I think, much sharper things about the economic value of those, and argue causality in a much more direct way than the kind of indirect way that we often end up having to argue it.
That's fantastic. Thank you so
Yeah.
much.
So feel free to get in touch
you
if
up on
you like seriously, if you have thoughts on that. That's the sort of thing that I would love to hear about.
Well, we are at the end of an hour and people are having to run off. This has been really great. I think you will get a lot of follow-up, and we may all have questions about a whole bunch of other things, including impacts on precipitation and winds and everything else that we also think about. So,
Yeah.
but thank you so much for sharing this with us. It's been great.
Absolutely. Thank you very much. Thanks, everyone. Thanks for the opportunity.